I mentioned earlier that we have all these positive particles in the form of protons in our nucleus. They're all positively charged. Positive charges tend to repel each other, yet the nucleus is held together as an intact, usually fairly stable entity. What does that is the binding energy, and that holds both the protons and the neutrons together in the nucleus. And the binding energy is comprised of the weak and strong nuclear forces. The larger the binding energy, the more stable the nucleus, because there's more energy to hold all these charged particles together. How do I figure it out? Well, Einstein is the one that came up with the relationship between the amount of energy created when an atom is broken apart and the mass of what is converted into energy. First thing I have to do is figure out the mass of the isotope I'm working with. And for a theoretical isotope, I'm going to take the sum of the masses of the protons plus the neutrons plus the electrons. And those values are given to you. They're in the back of the book once you get the book. In the worksheets, they are given, so in that you're working binding energy problems, you'll have the mass of the proton, the mass of the neutron, the mass of the electron to do the problem. If I'm working with oxygen 16, which is another way to write this isotope with mass 16 and charge 8. Oxygen 16 isotope is made up of 8 protons plus 8 neutrons in the nucleus and 8 electrons orbiting the nucleus. If I sum all those masses, what I get is a theoretical mass of 16 point all those numbers. AMU is atomic mass unit, and that unit is used because we're dealing with one atom. And if we were dealing with grams or kilograms, we'd have an exponent to either the negative 27 or the negative 31. So it's really tiny. So AMUs make more sense. Also, if this number is converted into moles, again, back to chemistry, it is the same in AMUs as it would be in grams per 1 mole of this isotope. Now, if I go out and collect a whole bunch of oxygen 16 isotopes from the air, from water hydrolysis, from a variety of sources, so I get actual real live oxygen 16 isotopes, mass them, what I find is the actual mass is not the same. It's 15.99, etc. Well, what happened? Why is my theoretical mass different than my actual mass? The difference between these two values is called the mass defect, and that's where the binding energy comes from. So the mass defect is converted to energy, and that holds the nucleus together. Again, if I want to find out how much energy this is, I'm going to use Einstein's equation. The mass in this equation is the mass defect. C is the speed of all electromagnetic radiation in air or a vacuum, and then the energy that I'm calculating is the binding energy. The energy here in this equation is energy per nucleus. So if I wanted to find this value, first thing I'm going to do is find the mass defect. So I'm going to take the difference between the theoretical mass and the actual mass, so I have 16. I end up with a mass defect of 137,441. Another way of writing AMUs is U. So U is a unit that equals AMU. It's just that sometimes scientists like a little bit less to write. Now I've got the mass, but this energy equation, I have to have my mass in more usable units. So I have to convert my mass in atomic mass units to kilograms. So I can do that, or we started working with electron volts in our last unit. We're going to continue to work with them. And the conversion here is 1 atomic mass unit is equal to 931.5 mega electron volts, or MeV, per c squared. So I've just taken the equation E equals m times c squared, solve for mass. So I have energy over c squared equals mass, and that's essentially what I've got here. So if I want to find the binding energy for this mass defect, I'm going to take the mass defect, and I'm going to multiply it by my mass to MeV conversion. When I do that, I get 128.026 MeV, and this is per nucleus. It turns out, however, that binding energy per nucleus is a helpful number, but not that helpful. What's more important is I want to know what is the binding energy per nucleon. Nucleon is a nuclear particle, either a proton or a neutron. So how do I find the binding energy per nucleon? Well, I'm going to take the binding energy per nucleus, in this case 128.026, and I'm going to divide it by the number of nucleons in my isotope. I'm dealing with oxygen 16. There's 16 particles because it has a mass of 16. So I have 16 nucleons here. And so that will now get me the binding energy per nucleon for my oxygen 16 isotope. And what I find is I have 8 MeV per nucleon. One more time, the larger the binding energy per nucleon, the more stable the isotope. So if we look at this chart, what we have is the mass number, so that's protons plus neutrons, on a horizontal axis, and we have the binding energy per nucleon on the vertical axis. The peak here, remember, as binding energy per nucleon increases, we get stability. We find iron 56 more specifically. As I go from large nuclei to smaller, more stable nuclei, I'm going through the fission process, breaking those large unstable nuclei apart. As I start down here with very tiny elements and slam them together to get larger nuclei, I'm going through fusion. Iron being the most stable isotope makes sense if you think about what our Earth, our planet, is made of. And our planet is primarily iron. The core of our planet is iron. Meteorites that strike the Earth are a large percent iron, probably because it's the most stable element based on binding energy per nucleon. Nuclear half-lives. Half-life is how much time it takes for the nuclear isotope, the radioactive isotope, to break down so that half of it is gone. So the half-life of a nucleotide is the amount of time it takes for half of the isotope to decay. The symbol that we use for half-life is T1/2. And we can have a huge range in half-lives. For example, polonium-214 has a half-life of 1.5 times 10 to the negative 4 seconds. So it's really short. It doesn't hang around very long. Uranium-238, on the other hand, which is the most common occurring isotope, has a half-life of 4.15 billion years. Okay, if we wanted to work through some half-life problems, a couple of equations that we want to use, or we can do it without equations. If we look at this particular problem, for example, we have element Z has a half-life of 3 days. We want to know what percent is going to be left after 3 days. If we start with 100%, one half-life means 50% is gone. That means 50% is left. If I'm interested in what happens and how much is left after 9 days, well, 3 half-lives is 9 days. 1 half-life is 3 days. 2 half-lives would be 6 days. 3 half-lives equal 9 days. So 50% is gone after 3 days. Half of that will disappear, so we're down to 25% after 6 days. Half of that will disappear, so 12.5% is what we're left with after 3 half-lives. You can also look at mass, you can look at counts, you can look at moles, you can look at atoms. So let's take a look at solving this. If I start with 20 grams of this element, I want to know how many grams will be left after 18 days. Well, 18 days equals 6 half-lives. So you can count through on your fingers like that, or you can use a log equation. And here's the equation that we can use. The way that we would use this equation would be to say N0 is my initial amount. N equals the amount at my time of interest. X is the number of half-lives I have gone through. So if we use this equation, we can set it up and solve as this. So I have the log. My initial amount is 20 grams. I'm looking for how much is left, so I'm looking for N that equals X. X is the number of half-lives. We determined just by counting that we had 6 half-lives. So when I go through the math, when I use the log button correctly on my calculator, what I end up is finding that I have 0.3125 grams left. And that takes us through chapter 25. Problem set will give you some practice with decay reactions, with binding energy problems, and with half-life problems.